Bonjour, je voulais tout d'abord remercier les organisateurs de la conférence pour m'avoir invité. Bon, la conférence sera en anglais, il m'est plus facile de faire de la physique en anglais. Toutefois, j'aimerais bien dire que vu que c'est un grand congrès avec des physiciens de tout genre, j'espère réussir à vous communiquer l'enthousiasme de ce genre de physique et ce qu'on peut découvrir à niveau fondamental avec les étoiles compactes. Ok, c'en est assez de français. Now we switch to English, which is a bit more natural for me. So this talk will be obviously a review talk, trying to make you understand why studying these amazing objects, and when I talk about amazing objects, I'm including supernovae, neutron stars, quark stars, hybrid stars, and we'll see what we're talking about. How studying those amazing objects, we can actually shed light to some very deep properties of nuclear matter, of space-time, of condensed matter, and so on. All right? So I will give you a quick outline of the lecture. I call it a lecture because actually it's general and it wants to be introductory. And basically I will try to answer those 5 questions. The first one, all of us being physicists, is what do we see, what do we know from observations? And I will try very quickly to let you know what the most recent observations are telling us about compact stars. From observation, we can immediately infer some properties, microscopic properties of compact stars. And so 2 answers, I try to answer 2 answers. Why do we say they are made of neutrons? And another thing is why the masses are limited, which is a very important point. At that point, we will be ready, we will have enough material to try to understand what the structures of the star is. And you'll see that the structure from the nuclear and subnuclear point of view is absolutely amazing, because we are going from the surface where we have dripped neutrons which are superfluid, and going deeper inside we get to very dense nuclear matter and possibly to exotic states of matter. And finally, just to make a contact between the more astrophysical and fundamental point of view to what we can really do with those stars, I will show you, I hope I'll make it with time, just 4 examples. I could give you many, many more, but 4 important examples of the kind of observation not just that we could, that we can, and we are actually making observing neutron stars, and what the consequences of those observations are. And as you see, we are talking observation about mass, about temperature, about gravity. So they are very standard, if you want, observation. But what we are looking forward and what we're trying to explain are things like the equation of state of dense bulk matter, properties of superfluidity, neutrino emissivity, existence of exotic states of matter, the structure of space-time. So you see that we start from those fundamental and compact stars, and then we go to much deeper issues. So let's start with observation. Here is a very beautiful picture, I believe, of the supernova remnant in Cassiopeia A. This is the remnant of a supernova explosion. I will not dwell very much, actually will not dwell at all on supernova explosion, but Thierry Foglietto, in a subsequent talk in one of those mini colloquia, he's an expert and will give you everything you want to know about supernovae. Anyways, the point of this picture is to show you how in the visible spectrum, in the optical spectrum, those objects are quite insignificant. I mean, who would care? Okay, it's a supernova explosion. And then look what it looks like in X-ray. This kind of astrophysics is part of the X-ray sky. So it's not surprising that it's a kind of recent astrophysics, because we can see X-ray not from Earth but from space. And so we need the time to send satellites in space and start to look at them. So inside the supernova remnant, which is quite dim in the optical, which is very bright in the radio, actually Cassiopeia is one of the brightest radio sources, and which is incredibly beautiful and bright in the X-ray, we have a compact object. And okay, leave alone the name CCO, it's just a classification of astrophysicists. But what we're going to talk about is this kind of object. So, observation. The effort has been enormous. I mean, lots of money has been spent, starting from radio telescope from Earth, and now we have satellite, Chandra, Swift, Newton, Agile are already working. Most satellites are programmed, and then also incredible arrays of radio telescope like the Square Kilometer Array, LOFAR. This is the effort, the observational effort, from which we will have the result we are looking for. However, we shouldn't forget that compact stars are interesting also in two completely different bands. One is the, let's call it band, the neutrino. We have already observed directly the neutrino from the formation of a neutron star and the explosion of supernova 87A. And the other one is gravitational waves. There are two amazing detectors, actually, one in Italy and the other one in the United States. And we, I mean the community of compact star scientists, are expecting to have results in the next few years. So it's the near future. So, observations. The first thing that was observed of those stars, although theoretically they had been predicted way before, is radio emission. The radio emission, I think this is the Crab or Vela, it doesn't really matter, because it can be very different. In this case, the radio emission stretches from radio to gamma rays. And as you see, there's a regularity. As a matter of fact, when averaged in the right way, pulsars, that's the way they're called, radio pulsars or pulsars for short, are the most accurate clock in the universe. They can be precise 1 digit in 1 part in 10 to the 12, 10 to the 13. And this has been used, and we see later, in different observations. The model, which was almost immediately proposed and which actually is a good guideline to see, to study them, it's simply that of a strong magnetic field attached to the pulsar and rotating. The electrodynamics connected to this is very complicated, but in a way you can understand that there will be a preferred beam of emission, and when the beam of emission hits us, we can see a pulse. And so that's why the name of the lighthouse model. You may wonder why we need a strong magnetic field and strong rotation. Well, when I'm going to talk a bit later about the evolution of the formation of those stars, you will realize, physicists realized that it's quite natural from the collapse of a large star to a very small object, from conservation of angular momentum and conservation of magnetic flux, to have those large values both for the spin and for the magnetic field. Another kind of observation, actually, let's put it like this. What is really characteristic of those pulsars is the period. I told you can be extremely precise, but also those stars are slowing down. So there's a deceleration of the rotation. And it's quite usual to put in a period derivative of the period graph. And I could say this is the zoo, what we see now. These are the standard radio pulsars, they're all bunched here. Then more recently, a whole different family, the millisecond pulsar, these are rotating very fast, were observed. And then there's those new objects, the ones that are visible pretty much only in the X-ray, that are called magnetars, IXPs. The point I want to point out is that with the lighthouse model I told you before, we can have lines of equal time. You see, this is, I can't read, but it's 1,000 years old, 100,000 years old, 10 mega years, and lines of constant magnetic field. Here we are talking about 10 to the 11 Gauss for the regular pulsars, 10 to the 12, but this family is going above 10 to the 14 Gauss, all right? And this is, I mean, I cannot go, of course, into details, but there are also different ways to understand that these kind of magnetic fields are really present, all right? Other kind of observation, masses. We're going to talk a bit later about masses. You see that many of those have been measured. So, well, these are the different techniques, how they're measured, but I will dwell about this a bit later on. What you can observe is that sometimes there are very large error bars, which is not very nice. However, there's a whole family here of stars. These are binary neutron stars, where the error bars are almost negligible. And it would look like all these stars have pretty much the same mass. However, I would like to point out this observation. This is from 2 years ago. Very small error bars. I'll talk about this one later. But anyway, this is evidence of a much heavier neutron star. All right? And as a matter of fact, a few weeks ago, a second one as heavy as this one was observed. Another kind of observation is temperature, surface temperature. Why? Well, these objects, we'll see a bit later how hot they are. But anyway, they have a hot surface. So one might expect to see the thermal spectrum from the surface, and indeed, in many cases, it's possible. What is actually plotted here is the surface temperature against the age of the star. You will notice the huge error boxes because somehow the determination of the age is model dependent. However, there are some exceptions. Casey, the object I saw you at the beginning, we know when it exploded. We know when it formed. It's between 1650, 1680, so the end of the 17th century. So almost no error bars. And also Puppis A is very small. All right? So we'll see later the importance of this. Just look at the scale. We are talking about units of 10 to the 6 Kelvin. All right? So energy-wise, we're talking about a fraction of keV. We're talking about soft X-rays. These are not stars you see with your naked eyes. You can see them with X-ray or gamma-ray telescopes. So now we can sum up the conditions. Of course, it's not from those 4 slides I showed you that we know those conditions. It's from 20 or maybe 30, 40 years of studies. But we are talking about objects which have a mass between 1 and 2 times the mass of the sun. Okay? Just to give you an idea, our sun has a mass of 2 times 10 to the 33 grams. And these ones, the ones that have been measured, stretch from 1 to 2. The radius, and this gives the name compact to those stars, is amazingly small. We are talking about 10, 15 kilometers radius. It's not larger than a big city. It means that you would take our sun, which has a radius of 600,000 kilometers, 2 light seconds, and compress it, compress it, compress it, compress it, compress it until you get to a sphere which has a 20-kilometer diameter. It's amazing. So it doesn't take a PhD in physics to find the average density of this object. And the average density, the average one, not the central one, is between 10 to 14 and 10 to 15 grand centimeter cube, when saturation density of nuclear matter is 2.8 times 10 to the 14. So we are talking about objects that microscopically are denser than ordinary nuclei on Earth. All right? The central density can go up to 4, 5, maybe possibly in a supernova explosion, maybe 10 times as dense as nuclear matter density. So you see, when I say extreme physical condition of those objects, I'm not using the word extreme lightly. These are really extreme, and I believe I've studied a bit of astrophysics on top of this kind of field. I think they are really the most extreme thing you can see. So what else is interesting? We talked about observed surface temperature between 10 to the 5th, 10 to the 6th Kelvin, which is around 0.1 keV, soft X-rays. But then also it's not difficult to infer the internal temperature. Actually, the difference all comes from the crust that is very easy to study. We're talking about 10 to the 8 to 10 to the 9 Kelvin. 10 to the 9 Kelvin, the 0.1 MeV. They are 100 times as hot as the sun is inside. The sun, when nuclear reactions happen, well, these are way hotter. About the rotation, the frequency, I told you they are spinning. And the range of frequency between 0.1 to 1,000 Hertz. So can you imagine, you take the sun, one mass, one solar mass, you compress it to a sphere of 20 kilometers radius, and then it may be spinning 1,000 times a second. Attached to this, tangential velocity is angular velocity times radio. We're talking about radial velocity that can be 2/10 of the speed of light. So you need electrodynamics, really good relativistic electrodynamics. You can imagine all the phenomena which are linked to this, especially when you have magnetic fields which are rotating like this and which have a strength of 10 to the 12, 10 to the 15. I have a lot of admiration for LHC and these kind of things we did on Earth. But when you look at the magnetic field, the highest magnetic field we can obtain on Earth, I don't know how many, 1,000 Tesla, I have no idea. Honestly, I don't remember the number. But you compare it to this is absolutely amazing. Those objects they emit radiation in many bands. They mostly emit radiation, well, let's not go into details. This looks a number which is maybe insignificant for you, but the sun emits 10 to the 33 erg per second. So, although these are not luminous in the visible, they are over 100,000 brighter than the sun. In a second, they emit 100,000 more energy than the sun emits, although there are no more nuclear reaction in them. All right? The final thing, you may want, this is a well-known parameter, if you're a specialist, it's the ratio between the Schwarzschild radius of the star, which in this case is 3 kilometers, and the radius of the star. But it's a parameter to understand how important general relativity is in this object. This is the adimensional potential. It's basically the ratio between the potential energy, the binding energy of the star, and its mass energy, mc squared. It's of the order of 0.1, 0.3. So they are not black holes. Black holes is the ultimate general relativistic object. But they are definitely objects that must be studied using general relativity, and as you will see later, will become interesting with general relativity. All right. So the origin of the neutron star, could take 10 hours to discuss it. Unfortunately, the picture is not so visible. But anyway, the idea is that gravity is playing the main role. Gravity, the only of the four interactions which is always and only attractive. It pulls in. And the game in stars is the continuous competition between the pull of gravity and the way nature reacts to this. How? With different forms of pressure. Initially just thermal pressure, then when it's not enough, but the system becomes hotter and denser, like in regular stars, our sun, nuclear reaction sets in. And all of a sudden, the original elements the universe was left with at the beginning, with the Big Bang, which is hydrogen, 3/4 in mass, and helium, starts to be fused into heavier element. And the whole history of stars is compression, nuclear reaction. Then at some point the fuel is over, so the star contracts again, new reactions are lit up. But then at some point you reach iron. When you reach iron, the most stable element, you can't extract energy from it anymore. And that's the beginning of the end. According to the initial, well, you can't see anything in this thing. I hope if you're interested, you will go see the slides on the internet. But anyway, these are light stars, these are medium star, these are heavy star. By light star, I mean stars less massive when they are shining as classical stars, less massive than 10 solar masses. Intermediate stars are between 10 and 25, and heavy stars are above 25. Okay, light stars below 10 solar masses usually evolve to a compact object which is called white dwarf, which is quite amazing in itself, but not so exotic. We are talking about extreme structure of matter. We have properties of matter that are real beautiful, but from the point of view of nuclear physics, of subnuclear physics, of fundamental physics, it's still matter the way we know it, although pushed to the extreme. So the end point of all of these are white dwarfs. The end point of the very heavy stars are black holes. There's nothing that can prevent collapse of the star to a singularity. There's no form of pressure or of reaction of whatever that can prevent them from collapsing within the Schwarzschild radius and therefore collapsing to the final singularity. And then in between there's this class of stars which are reasonably common. Betelgeuse in the Orion Nebula is an example. These are the stars that will evolve they will evolve through the typically supergiant phase, and then they will bloat, and then they will explode. These are the stars we're interested in. They will explode in a supernova explosion, and then finally, what will be left over is the nucleus. Most of the star will be expelled in the supernova explosion. If you remember the first transparency I showed you, there was this big thing, which is basically the cloud of ejecta, which were expelled by the explosion. And what is left in the middle is a compact star. So this is the object we want to study a little bit more, okay? So the origin of compact star is interesting. Unfortunately, I can't go much deeper into this, but there are two physical points I would like to emphasize. What is the difference of studying compact star as compared to studying anything else in the universe, probably? Compact stars are the only place where the four fundamental interactions play on the same level. Strong, weak, electromagnetic, and gravitational interaction play on the same level. It's the first time that gravity counts. I mean, in 99% of the physics I did when I was a student, you do LHC, and who cares about gravity? G, acceleration of gravity, 9.8 meters second square. Who cares? It's absolutely not interesting. Or you go to the other side, the universe globally, and then it's only gravity and electromagnetism. Who cares about short-range interaction? The weak and the strong interaction, okay, they're responsible for nuclear interaction. Here, in those stars, the four interactions play at the same level. And so basically, studying compact stars is in a way going and seeing what is the effect of strong gravity. How does it change the game? The first way strong gravity changes the game is changing the nature of matter. Matter, we know it, all right? We know this is the table of elements, number of protons, number of neutrons, stable nuclei, all the beautiful thing of nuclear physics. We know that here are the stable nuclei. We know that we have isotopes that are richer in protons on one side or richer in neutrons on the other side. And then we know that going further and further, we have what we call the drip lines, proton drip lines or neutron drip line. The neutron drip line is when the nucleus is so full of neutrons that at some point neutrons start to drip out. Of course, from the experimental point of view, this would be beautiful to reach, and I really hope that in, I don't know if in the near or a bit further away future, but that sooner or later we'll be able to explore in accelerators, in heavy ion facilities, like you have one of the most important here in France, you have Ganil, okay? We'll be able to explore this region. But supernovae and neutron stars, compact in general, allows us to go way further. Supernova allows us to study this region. We are not yet to neutron drip, also because supernova consists of dense matter, but dense hot matter, while the other one will be dense and cold matter. But still, supernova, you can go and see what the effect of weak interaction is, and neutron star can go, as we'll see later, well beyond the neutron drip line. So what's the idea? The idea is that if you take a neutron, you put it here, you wait on the average 11 minutes, and it decays into the proton, which is lighter, and the electron, and the neutrino that goes away. And of course, you don't expect that if you take an electron and a proton, they will fuse, or better, that the proton will capture the electron. Why? Because you have a difference of mass between proton and neutron of 1.29 MeV, and the mass of the electron 0.5. So you still have an energy deficit of 0.8 MeV. So the capture is not possible unless, for some reason, the electron has enough kinetic energy to give this mass difference. And in a dense environment like the neutron stars, dense environment, because as we see, the state of matter is degenerate. Here we have not classical stars, we have quantum stars. Basically, although the temperature is almost 1 billion degrees, it is as if, compared to the density, as if the temperature was zero. So we are really talking about a structure where particle fermions are occupying all the states according to the Pauli exclusion principle, all right? And so we know that relativistic degenerate electrons have a chemical potential which is related to the Fermi momentum, and basically goes like the density to the 1/3. So if gravity gives you large densities, and that's only, gravity can do only that, it can only compress. If you have large densities, you have large potentials, chemical potentials for the electron, and if you have a large chemical potential for the electron, this reaction, whose chemical equilibrium is given like this, is shifted to the neutron side. And then the basic idea is, if gravity compresses, the result is neutronizing matter. Electron gets captured by free protons, electron gets captured by nuclei, as long as nuclei are present. So this is the first important thing. The other important thing is here, under relativistic degenerate conditions, you cannot go much higher than one solar mass. This is an argument due to, in this case, to Landau for finding the mass. It just depends on something like what I told you before. The gravitational energy per particle goes like 1/r. The internal kinetic energy per particle of fermions goes again, if they are relativistic, like 1/r. So the total energy goes like this kind of combination. And you see that for small masses, this quantity is positive, and then you have this kind of behavior, a star which has a minimum stability. But for large massive, this term prevails over the other one, the total is negative, so the behavior is this one. No stability collapse. So we know from fundamental physics that not only those stars will be neutronized, but they cannot have a mass as big as we want. Actually, more than 2-3 solar masses is even totally prevented from general relativity, which explains why we have such a narrow range of masses. So let's go a bit further. We have understood those stars, we have an idea of how they form and what they are. Why are they interesting? This is the phase diagram of hadronic matter. What's hadronic matter? Matter. All the matter we have on Earth is hadronic matter. We live on this side, on the confined side, where quarks doesn't like to be alone. They are color-free, so we have triplets, these are baryons, or particle-antiparticle, quark-antiquark, which are mesons, which transmit the interaction, okay? And here we have the other sector, the quark-gluon plasma, all right? And we know that the dream of a hadronic physicist, the dream of every physicist who wants to know what's matter, what's its structure, is to explore this plane. And if you want to explore here this part of very hot and not dense matter, okay, here you have cosmology, the Big Bang, the initial explosion where you have extremely high temperature and low densities, because we're talking about the universe. Then here there should be a phase transition, and the big accelerator, GSI, Ganil, which is not here unfortunately, RIC in the United States, LAC, are used to probe these regions. But there's absolutely no way now in the future that we will be able on Earth to probe this region, the dense and cold part. However, we have compact stars. We have neutron nuclei are here, baryon, this is saturation densities. If we go all the way to here, this region is probed by neutron stars. And here we may have the transition, the deconfinement transition to the quark-gluon plasma, or we might have here color superconductivity, coupling of color, like the pairing in nuclei or like the superconductivity in metals, but with the color degree of freedom. So it's a fascinating field, and indeed, from the point of view of hadronic matter and compact stars, theories, you know, you give theorists a little bit of leeway and they go crazy. So they have proposed every kind of star. I will not dwell on this. I mean, we have hyperonic stars. If you have enough density, hyperons will appear, exactly for the reason why electrons are captured. I mean, you have enough energy given from density. Or you may have strange stars, stars that are made of deconfined quarks all the way except for their crust. Or you may have exotic condensate, kaon condensate, pion condensate. But let's stay on the simple for now, okay? Let's stay on what we are pretty much sure about. which is this sector, the neutron star. All right? So, although compact stars sort of defines a very large class of objects, the one I could put my hand on is neutron star, possibly, actually, probably with hyperons inside, and maybe, but that's a big maybe, which may be sorted out for a future observation, maybe an exotic core. So, what's the structure of a neutron star? Well, like every object, we know the Earth has a structure. We have a crust, we have the mantle, we have the core, the liquid core, and blah, blah, blah. Neutron stars have a structure which is determined by the density. They are dense inside up to 2-3 times nuclear saturation density, and density goes to 0 on the surface. So we start with a regular outer crust, nuclei. Which kind of nuclei? Well, the most stable one. These stars have 10 million years since formation to evolve and get thermodynamic equilibrium, nuclear statistical equilibrium. So this will be probably iron, and then we will have possibly an atmosphere of helium and hydrogen. But then we go deeper, we go in the inner crust. And in the inner crust, that neutralization process I told you has gotten really to a good point. In the inner crust, I have coexistence of clusters, nuclear clusters, but with dripped neutrons. So the nuclear clusters, which I can tell you, I mean, now I don't remember, but we may have 10, 1,000 and whatever. I mean, they are not what we see in regular nuclear physics, but they're something that exists in nature, probably. Actually, on this, now the community is quite sure, because here we are in a region below nuclear saturation density. So the equation of state and the models we do are reasonable enough that we can believe this. So here we have a region of exotic nuclei permeated by a gas of unbound neutrons. And then when you go here inside, you may have exotic nuclear shapes. You may have pasta phases like long rods or plates. All these are understudied. There was a Nature paper a few weeks or days ago about the influence that those pasta phases may have on the cooling of stars and so on. Then here you get on saturation density, so matter, hydronic matter, melts into what we call nuclear matter, but it's only here that nuclear matter has saturation density. Here it goes denser and denser, and so possibly, we don't know where yet, and we would like to use neutron stars or compact stars in general to understand it, there may be an exotic core. And look at the proportion. We have out of a star, which we may have 12, 11, whatever, kilometers radius, most of it is the nuclear core. But then there's this thin, it's about 1 kilometer crust. And the crust is very important because whatever happens inside has to go through the crust to be seen. So ready? No. All right, so this is the object we want to study. It's very complex. I will not dwell much more on this. There's many phenomena. So let's see what we can do, what has been done. First point, the holy grail of nuclear physics, the nuclear-nuclear interaction. We all know it has an attractive part, a repulsive part at close distance. What's the bridge to astrophysics? How do we connect this with astrophysics? We connect it because once we know the properties of the nuclear-nuclear interaction, we can build an equation of state, the relationship between the pressure and the density of energy. We have some limits, but the point is, different nuclear-nuclear interaction give different equation of state. So this is something we can use and test. And you see immediately how you can use and test. You can take the equation for relativistic equilibrium, the so-called Tolman-Oppenheimer-Volkoff equation, and solve them and find, given some mass, what the radius of the star will be given an equation of state. And you see, theorists have proposed in the last 50 years hundreds of equations of state, and so you have hundreds or tens of curves. Some behave differently. This is quark matter, so it's a way to distinguish them. Some are very different. By all of a sudden, you see that all those curves have a maximum. Take this PAL 6. PAL 6 predicts that the heaviest star can have 1.5 solar masses. Or PAL 1 predicts that the heaviest star can have 2.5. And here we have observation. I told you, up until 4 years ago, the heaviest star was about 1.5 solar masses. So basically, this was this level. All those equations of state that don't reach this level were ruled out. But now we're here. The latest observation is 2 solar masses, which kills all of this. So observing the masses of neutron star can tell us so far not which equation of state is good, but for sure which equations of states are bad. And as a matter of fact, most of them are bad and don't work, all right? The ideal thing would be to find for a star at the same time its mass and radius. This would give us a position in this plane. But observationally, for the time being, it's almost impossible. Other thing, cooling of neutron stars. Neutron stars are formed as hot objects from an explosion, and they cool. How do they cool? Well, you would expect them to cool because they're hot, and every hot object put in the vacuum emits electromagnetic radiation. Of course they do emit, we saw in the X-ray. But these stars actually cool by neutrino emission. The inside of the star and part of the crust emits neutrino at an incredible rate. So this whole central part you see from 10 years to 100,000 years of age is neutrino cooling, all right? Then there's differences between rapid cooling or fast cooling. What's the idea in all this? The idea is very simple. We have some objects, you see them with error bars. Some are young, some are older. Again, like before, this is time from formation, this is temperature. So you have some kind of a correlation between temperature and time. And so you would like to find a microscopic model for the crust, for the core, for the emissivity, for the properties of matter that can fit those stars. Here you see just what happens changing the mass of the star. With the same mechanism for cooling, as the star gets heavier, it gets cooler. So you see that studying the cooling of neutron star can be a direct probe to study the weak interaction phenomena in this case, because it's neutrino emission that happen in their cores. And this is something I have to mention it. Casey, the star we saw at the beginning, just last year, we saw it cooling. This is years, 2000, 2002, and 2004, and this is a temperature which is going down. We have seen a star not only shining, but shining and cooling. And actually the study, there were lots of studies, but the idea is that it looks like the cooling in this region and in this region has not the same rate. And it has been speculated, probably quite convincingly, that around here, superfluidity sets in. And so we may have direct evidence of superfluidity affecting the cooling of the star and seeing it here. And I'm talking about nuclear superfluidity, not electron water, not the BCS theory of metals. We're not in those conditions. Another thing, this is my field of expertise, glitches. Those stars are slowing down. And then all of a sudden, let's say that all of a sudden they speed up. It is as if you have a sphere in the space, nothing is around it, it slows down, and then all of a sudden, or you take a top, something which is spinning, you don't touch it, and then it's slowing down, and then all of a sudden it speeds up. Okay? This is quite amazing. The speed up can be 1 part in 10 to the 5th, and if you see energy-wise, it's an enormous amount of energy. Well, the interesting thing of glitches is that, according to a view which is now quite established, there are probably evidence that neutron stars are kilometer-sized superfluids. You may say, well, superfluids, I mean, this is zero temperature physics. This is what they do in superfluid helium and everything. Yes, because superfluid helium is not dense. Here matter is dense. And so actually the temperature, although it's high, as compared to the Fermi temperature, is almost zero. We expect nucleons to be paired and to have all the phenomena like superconducting protons in the core of the star and superfluid neutrons around. And we believe the glitches are evidence for this. Pas très long encore. I will not go into detail. The idea is, this is marvelous for people who do condensed matter, because superfluids rotate in containers, helium-3, helium-4. Here we are closer to helium-3 because we have fermions, not bosons. So we have formation of Cooper pairs. Anyway, when a superfluid rotates, it doesn't rotate with like a rigid body. It must be rotational. So it rotates by building up an array of vortices. Vortices like, you know, tornado, but vortices are macroscopic in this direction. They can be 10 kilometers long, and in this direction, transversal, they are 10 Fermi radius. So it's a very strange thing, and the angular momentum of the star is quantized in vortices. And so if somehow vortices get stuck to the crust, then they're not free to slow down. And they only slow down when the tension is very strong. So in a way, those glitches would be the evidence of superfluidity, because the vortices carrying the angular momentum of the star gets attached to the crust for 3 to 4 years, and then there are hydrodynamical forces that detach them collectively, and they transfer the angular momentum to the crust itself, and we see the speed up. The last thing I will discuss very quickly is gravitational waves. Gravitational waves are something that is one of the great predictions of Einstein's theory of general relativity. I mean, we know from electrodynamics, you take a charge, you oscillate. If it has an acceleration, it emits electromagnetic waves. Well, Einstein's theory predicts that if you have a mass, quadrupole mass, but it doesn't matter, let's not go into details, and you oscillate or move it, it will emit gravitational waves. What are they? They are ripples in the space-time. It means that 2 points in space-time will change their position, the length will change. And so the ideal place to study this, to study those general relativistic effects, is in binary system. Stars don't like to be alone. I think that more than half of the stars we see are in binary systems. So it's not surprising that compact stars are in binary systems. And we have seen several, but two pulsar systems. Here I give you just 2 examples. This is a famous example a few years ago. It's an amazing test of general relativity, because you have 5 post-Keplerian parameters for who knows general relativity, and actually you fix 2, and then the other ones, if the theory is right, will give you a mass. Well, I'm talking about the determination of the mass. Here you don't see the figure, but we have 1.338 solar masses. We are determining the mass of the system using general relativity and testing general relativity with a precision of better than 1 per 1,000, which is in astrophysics is incredible. And this is very recent. Last year, the 2 solar masses, this is called Shapiro Delay. Basically, it's a neutron star and a white dwarf. And as the neutron star goes behind the white dwarf, its emission, the pulse emission, has to go through the gravitational field of the white dwarf, and it gets delayed. And you can measure this. You see, these are the signals. This. If there was no gravitation, it would be a flat thing. And this is the effect of the compact star being behind the white dwarf, and here it's in front of it. And from this we found that 2 solar mass star, which is ruling out so many equation of states. And the last slide is this. We have seen gravitational wave. The Hals-Taylor pulse have been observed for 30 years, and these are the observed points of the slowdown. The star is emitting gravitational energy. It's losing energy, so it can only slow down its rotation. The prediction of general relativity is the continuous line, and this was worth a Nobel Prize to Hals and Taylor, so it looks like a graph, but it's something more than a graph. And then the future. The future is not that far away, 2017. Hopefully we'll all be alive and still working and everything. We expect that merger of those stars, you see a binary system emits energy, they lose energy, so the star gets closer and closer, and at some point they will merge into a black hole. And this is the best way to produce gravitational waves. One could say, who cares if I'm not interested in general relativity? Well, the signal, the template we expect to see in those detectors depends on the equation of state of matter inside the star. And so basically, this will be the ultimate probe, looking at the behavior of matter at high density directly through the structure of space-time. So I finish here. Unfortunately, I could go on for 20 hours until I bore you and kill you. But I have to tell you about ComStar. Well, I have to tell you first this. As you have seen from my talk, studying compact star is one of, not the most interdisciplinary subject, but one of the most interdisciplinary subjects. You need astrophysics, of course. We're talking about astrophysics, and you also have to study those phenomena that happens with strong magnetic field rotation and stuff. You need gravitational physics, gravitational waves. We talked about that, the structure of space-time. Of course, you need nuclear physics. You have to know what you are talking about. So these three fields of expertise are needed to study them. And a few years ago, well now almost, well whatever, 2008, when I say we, I'm talking about myself, people from all over Europe. Here we have three people who belong to ComStar, Jérôme Margueron, Thierry Folitz, and Francesca Gulminelli. People coming from different fields. We have a pure astrophysicist and two nuclear physicists. We have had money from Europe, it's always useful. We ran for 5 years. We were quite successful. I shouldn't say it since I'm one of the coordinators of this, but we are becoming a label in the field of nuclear astrophysics. I mean, a label also abroad in the United States, in Asia. ComStar is started to be known. On the 15th of May, we were funded in a new initiative, which will go on for 4 years. So, of course, I invite, if there are students here, to have a look at this physics, because I think you have noticed, whatever you like gravity, okay, it's here. You like condensed matter, you have superfluid. You like nuclear matter, of course, this is your cake. You like astrophysics, emission, pulses, magnetosphere rotating, here it is. Then I didn't talk about accretion, X-ray pulses. I mean, it's really something that can give satisfaction to everybody. So you can have a look at this side. This is the site of our old network. We have the first meeting of the new network, and I think you will hear about us, hopefully. Anyway, thank you for the attention. I'm sorry if I went a bit too long with the time.